So this would be the concluding lecture on as we review the overview article on computational understanding of lithium-ion batteries by Ceder's group, right? So this lecture is, the topics that are to be covered are more to do with thermodynamics rather than quantum mechanics. Okay, so the whole objective is to point out it is possible to connect properties computed via DFT. Okay. Usually we are thinking about binding energies and so on, right? So how do we go from here to properties of thermodynamic quantities, all right? Thermodynamic quantities. It is possible to do, and all the prescriptions, at least cannot be done in this lecture. Maybe at a later stage we can talk about that. Okay, so here, see, the main thing is what? How do you go from here? You have to have a notion of how do you think about temperature, okay? That is the main thing. And then, so even without introducing, there are some formal ways of thinking about temperature from quantum statistical mechanics, okay? So we are not going to do that. So what we would try to do is, we would talk about, in this way of modeling things, we would talk about thermodynamic quantities, and certain information, certain parts of this information would be obtaining from density functional analysis, okay? So what kinds of questions we'd be interested in answering? So for example, thermal stability, all right? So if you're thinking about thermal stability of cathodes typically, so what is the issue here? For example, when you have, let's think through this problem slightly chemically, okay? So we have a very relevant topic of current research. So we have something called, see, if you want to get more, so to say, bang for the buck in a lithium-ion battery, you should be able to load the cathode with more lithium, okay? So this is called lithium excess cathodes. So when you do that, there are certain complications, okay? Or when you are oxidizing a cathode with lots of oxygen. So let's consider the case, all right? So what might happen is, let's understand this situation here. So if you look at it from thermodynamics point of view, the greater the temperature, the entropy of this system, okay, the entropy of products here is always more than the entropy of this system, because it has a more number of, see, this is in gas phase, okay? So if you, so for this you have to know certain amount of statistical thermodynamics or chemical engineering thermodynamics. Anyway, so I'm not going to do that here. So take it for granted that this has greater, the products in this case have greater entropy, okay? Especially because of this being in the gas phase, okay? The number of moles, see here you have, let's say 1 mole. For every 1 mole of this cathode material getting decomposed, you get 1.5 moles of product material, okay? This is what is going, this in the gas phase is what is going to contribute, okay? For example, when you have H2O, okay? at room temperature, water is stable. But when you keep increasing the temperature, there's thermally it dissociates. Why does it dissociate? Because the one H2O is going to generate one H2 plus half O2, okay? 1.5 moles of molecules of gas molecules are going to be produced from one H2O, water vapor, at high temperature. So as the entropy is greater, we have G is equal to H minus Ts, right? So increase in temperature will favor between these two things, will favor uh, the products, okay? Because at low temperature, you always have systems which have, overall, what is that we want to do? We want to minimize that, okay? Minimize free energy. So what are the two approaches? In fact, at low temperatures, this is getting minimized. At high temperature, you try to minimize free energy by minimizing this. You try to favor the reactants or products which has higher entropy. Okay, so at low temperature, this contribution, Ts contribution, is less to free energy. So you are generally trying to look at reactants or products that are lesser enthalpy. All right. So at high temperature, Tx contribution becomes significant. So another question we want to answer is, so usually you think about the temperature driven degradation of these kinds of compounds. So if you think about this compound, what is that? Why does it prefer to decompose? And if you look at it, oxygen is a very electronegative material. So if you over-oxidize a cathode, the oxygen would like to have lots of electrons, and the cations in the cathode are not able to provide enough electrons for the oxygen. Okay, so oxygen would try to just prefer a homonuclear diatomic molecule, just O2, okay, form a covalent bond instead of obtaining electrons from the cations. Okay, so the cations have low ionization energy. Oxygen has high electron affinity. That is, the addition of electrons to oxygen is exothermic. Okay, so but beyond a particular stage, oxygen is not capable of is not satisfied getting electrons from the cations, so it just prefers to decompose. Okay, this material gets to an extent, the remaining material, the remaining oxygen in this material can get electrons from these cations, but some part of the oxygen goes off as goes off to gas phase. Okay, so this is a very, very important problem in designing cathode. There are we want to model this system. Okay, so typically you don't in the DFT there are how do you go about doing this? You approximate this G of this reaction. You typically don't calculate H. Okay, H is equal to U plus PV. For solids, this PV contribution is very small compared to U. So you approximate this by just calculating energies. Okay, so all right. So for this system, it is up without calculating enthalpy. You calculate in the gas phase. Okay, this is in the gas phase. Minus, this is, we are explicitly, this is just a thermodynamic expression. Okay, this is nothing to do with quantum mechanics. Okay, so you are at a particular partial pressure of O2 at a particular temperature. Okay, this is nothing to do with really quantum mechanics. What is that we are trying to say? We can get this from DFT. Okay, what are the things which we can get from DFT? In fact, all these things can be obtained from DFT. For understanding, this is just like binding energies. Okay, so this is not a big deal. All right, so internal energies, you can, you can easily do a calculation. But what you have to know a little bit more on two aspects. Okay, so one is, how do you get entropy? Okay, so there's a connection uh, between macroscopic uh, thermodynamics and molecular microscopics. Okay, so this connection is made, this is okay, here by S I mean entropy. This connection is via statistical thermodynamics. This is a course that is offered as a UG elective in chemical engineering. Physics department offers this, chemistry department offers this. So there are lots of departments which offer this course. So you should try to take such a course sometime before you graduate. All right. So why do we make this connection? Okay, this is what is accessible via quantum mechanics. Okay, how do you go from microscopic properties, binding energies, bond energies, to macroscopic? This prescription is via statistical thermodynamics. So that is not the scope of this class. I mean, some people who are doing projects on, let's say, cluster expansion, they would get a better feel for this. The another important aspect which I want to emphasize is, I'll give a separate lecture. Okay, this is one of the important issues. Okay, is on what is the biggest approximation in DFT? Okay, so see what is that? So this Consham orbitals. So there was a question in the discussion hour. Okay, Consham orbital. What is the advantage? Advantage is it gives you, once you frame something as an orbital, it gives you an expression for kinetic energy. Okay, so you know the Coulomb energy, Coulomb expression for in the Hamiltonian, you know the expression for Coulomb energies. Okay, attractive interaction between nucleus and the electrons, and the repulsive interaction between electrons. You know that. The other thing is within the Born-Oppenheimer framework, kinetic energy of nucleus is zero. You need the kinetic energy of electrons. So once we have the orbital, I know the kinetic energy operator. Okay, so that is, and then you are expressing the electronic density in terms of Consham orbitals. Okay, so this is the Consham prescription. This is not so much of a approximation, but the central approximation we are going is in exchange correlation potential. Okay, so this is what I don't know how to compute. Okay, so this is where the LDA, GGA, hybrid functions, all these things, this is the biggest approximation. Okay, this is the biggest source of error. Okay, so especially in some systems, okay, what are called strongly correlated oxides. Okay, and then even O2, okay, which is looks like a very simple molecule. Okay, which is there are issues. Okay, O2 is paramagnetic, and there is something called the self-interaction error. I will do a brief lecture on this. Okay, this is an important problem, and there are methods to correct the self-interaction error called LDA plus U or GGA plus U. U is this Hubbard parameter. Okay, so I will give a lecture on this. Okay, this important thing, that important aspect of DFT that you should know. All right. So okay, so what is that? Just to summarize, this connection is made by the statistical thermodynamics. That is, I want to compute this energetics, I need entropy. Okay, so to know entropy, I should know some statistical thermodynamics, which once you know that connection, you can take the properties that are computed via quantum mechanics and connect it to entropy, okay, macroscopic properties. Then so this is not an approximation. Okay, I just told because I want to emphasize why we use Consham orbitals. Okay, so Consham orbitals have the biggest advantage in that it kinetic energy of the electrons is known. And then using kinetic, the square of the Consham orbital is going to give you density multiplied with the charge of the electron. I can assemble the electronic density using Consham orbital. Then the single most biggest approximation is how do you get exchange, okay? Because electrons are fermions, there is something called exchange interaction because of fermions. And then there is something called correlation part, okay? So see, typically the single slated determinant, that is the simplest approximation that is there in Hartree-Fock approximation, okay? Beyond, you can go beyond the Hartree-Fock approximation via what is called configurational interactions, okay? Configurational interactions in the ab initio approach, okay? This is not DFT. That is, see, in the whole DFT, no slated determinant, no slated determinant. Right? So why do we use slated determinant? As soon as you enforce that your many body electron wave function is a slated determinant, the fermionic nature is met. Okay, so that the electrons are fermions is incorporated via a slated determinant. Because Consham orbit, I mean in DFT, we are using Consham orbitals. Okay, this is like a Hartree orbital. Okay, Hartree approximation. Okay, Hartree approximation, you know, this product wave function. So this slated determinant is not there in DFT. Okay, so there is this entire approach. Okay, in the see in 1999, I think. Okay, so the Nobel Prize was given to Walter Kohn, who developed DFT, and there was a quantum chemist called John Pople, who developed what so-called quantum chemical approaches or called ab initio approaches. Okay, so here the starting point is Hartree-Fock, okay, and a slated determinant. And then you can go to incorporate better correlation interactions. You use more than one slated determinant to express your system. Okay, so all these things are not available within DFT. We cannot have get the exchange interaction correctly, because if you use a slated determinant, that is the exchange interaction can be computed correctly. Okay, this is all I'm just quoting. Okay, like a mantra. I'm not explaining this. There was some in the MIT OCW class. Some aspects were dealt with. You might have heard it. But I'm not going to hold you responsible for you to know that. This class is mostly to do with DFT. All I'm saying is both these things cannot be dealt within DFT very easily. Okay, so that's the biggest source of error. So that there are ways of addressing this error. So eventually, when you do all these things, what is that you try to do? You obtain phase diagrams. Okay, so this is like what you see in chemical engineering classes, right? So this is nothing. See, like. So this you must have seen in all your material science classes or chemistry classes or chemical engineering classes, how to compute phase diagram, right? So what is that you try to do? First, phase diagram has a typical two things, right? One is pressure and temperature, okay? So pressure is usually atmospheric pressure. That's not a big variation. A variation in pressure is not incorporated, but variation in temperature is what is thought about. So what is that you plot? How do you plot phase diagram? So this is oxygen. So as when you have, so you might have seen ternary phase diagrams and so on in your chemical engineering classes. So this is all a lot to do with thermodynamics. Okay, so I'm not going to do these things here. So you as a function of oxygen partial pressure, and you ask, and let's say some other compound, let's say cobalt oxide. Okay, so you try to ask at a given pressure, which is atmospheric pressure, typically at a pressure and temperature and chemical composition, as a function of these quantities, what is your stable compound? This is the question you try to answer via phase diagram, right? So see, what is that? We are trying to ask this question, right? So if you look at what is the question we want to answer, whether is this stable or is this stable, okay? So intuitively, you can get an idea, right? So if you have a very oxidizing atmosphere, okay, so I would say the chemical potential, you should know, have an idea of these expressions are there in the paper, or these are more to do with chemical engineering thermodynamics. I'm not going to talk about this. I mean, if I have an oxidizing atmosphere, what do you mean by that? So if I have more and more oxygen partial pressure, I'm going to favor this thing, okay? I'm going to oxidize the product. If I have a reducing atmosphere, that is, if I have less and less oxygen, okay, the oxygen partial pressure is very less, I'm going to get to this thing. Like it's like you may think about a simpler system called like corrosion. Okay, if I have iron uh, under very reducing condition, if that is, what is the reducing condition? See, you can try to look at this. Like try to understand via corrosion. Okay, so reducing condition means less O2. Okay, you can have just iron. Okay, uh, pure iron is stable. Okay, pure iron is stable. Okay, but if I have oxidizing condition, that means more oxygen, then I would have Fe2O3. First, the surface of iron will get corroded. That is, I'll form an oxide, uh, and so on. Okay, so if I don't want to have corrosion of iron, I should not have. I should protect the iron, not expose the iron to oxygen. I can use a barrier coating or something, or not exposed to oxygen atmosphere itself. The oxygen can be oxygen, or the oxygen atmosphere can be provided by just water also, right? If you have water, iron need not get the oxygen from O2. Iron can get the oxygen from oxygen available in O2 and get oxidized. All right. So think the processes we are talking about are very similar to what you might be familiar in via corrosion. Okay. So that's the question, and there are ways to compute the phase diagram. Okay, and then you can compute how much of oxygen can be lost if I have, let's say, a cathode material called LFP. Okay, lithium iron phosphate. This is one of the common cathode that are used in your cell phone and so on. I can ask the question at different temperature, how much of oxygen is being lost. The greater the temperature, more of oxygen is being lost. At low temperatures, you typically, because the entropy is not favoring losing oxygen, you don't lose oxygen. As the temperature is increased, you typically start losing oxygen. All these things can be computed via DFT. So DFT, we've discussed this in terms of cathode, but this is a very economically important process, corrosion. Okay, so lots of research has been done how to use DFT to model corrosion. Okay, DFT to model corrosion. So all right, so I mean we cannot do everything under the sun within this course, but this is an important thing, and this has a lot of one of the biggest applications of DFT is to model corrosion in a variety of conditions. Okay, so this has been done. All right, so the last topic I want to talk about, if you see the only one component, we talked a lot about cathodes because it's sort of a very intricate system. Anodes is simpler. Okay, you use either a graphite. Okay, there's not the complexity of cathodes is way more than complexity of anode. Okay, so the last part is electrochemical stability of of electrolytes. So the traditional electrolytes are organic solvents. Okay, so organic solvents are the typical electrolytes that are being used. Um, uh, so now people are trying to explore a lot more solid state electrolytes. What is the biggest advantage? Solid state electrolyte help you suppress dendrite. Okay, so if I the lithium from the anode, when you fast charge the lithium ion battery, dendrite formation is a big problem. That is, the anode gets shorted across the cathode. The lithium dendrites go cut across and touch the cathode. Okay, so instead of the battery discharging via an external circuit, there is a direct connection between anode and electrolyte. That's one of the reasons why lithium-ion battery burst. Okay, so but the traditional, the people are using solid-state electrolyte to suppress dendrite formation. But the traditional electrolytes, okay, still what you have, the lithium-ion battery that you have in your cell phone battery uses liquid electrolytes. So one of the important question is to ask is how stable these electrolytes are. Okay, so what do you mean by that? Okay, so if I the question we are trying to answer is okay, so let's go back to this thing. For example, let's think about a simpler thing. In a lead acid battery, you have it's an aqueous battery, right? H2O. The thermodynamically, you might have heard something called water electrolysis. This can, if I this can decompose into this system, right? So the minimum thermodynamic potential, that is EC minus EA, okay, that is the potential of the cathode minus anode. The minimum is 1.23. So usually when you have the difference between anode and cathode just 1.23, it doesn't dissociate. But as it increases, say to around 1.6, then the water dissociates, all right? So these aqueous systems have a certain limitations. Okay, so you cannot have high voltage battery, whereas in a lithium ion battery, the your battery voltages are about 3 ev. Okay, 3 volts. Okay, so you cannot use aqueous water. Okay, so you typically use organic solvents. You try to ask the question. So what is the voltage window? So here the voltage window of stability of aqueous compounds is, let's say, below 1.5. Okay, so likewise you have organic solvent, non-aqueous organic solvents, non-aqueous, these are all non-aqueous electrolytes. Okay, so you ask the question, what is the voltage window within which these things are stable? Okay, so for stability. Okay, that's the question you try to ask. So here, what is that? So if I have here, when I say H2O is getting destabilized, okay, unstable means there is an oxidation occurring and there's a reduction occurring. Okay, typically if you split it down, there are two processes, right? So on if I do water electrolysis, there are two things that are occurring, right? At the anode, so there is a reduction process. Let's say you do it in acidic medium. Okay, so this is the reduction process which is giving rise to H2. Okay, or the oxidation process is so you have two protons and half O2. Okay, plus 2 electrons. Okay. All right. So at the anode, okay, there is this process, okay, of forming two protons, and at the at the see, there is when H2O dissociates. Let's understand. This is at the anode. When H2O dissociates in, let's say, in an acidic medium, two protons go into the electrolyte, oxygen gets evolved, and the two electrons go via the external circuit, external wire, and these two electrons go and reduce the protons available in the electrolytes to form H2. Okay, so this can be there is a reduction potential involved and an oxidation potential. Okay, the two reduction potentials. I mean, there's two processes. Okay, one is a reduction process, another an oxidation process. And see, all the in the electrochemistry only reduction potentials are defined, right? So you want to know the reduction potential for these two processes. There's one is a reduction process, another is an oxidation process. Likewise, here also in an organic solvent, which used in lithium ion battery or many of these high voltage batteries, there is an oxidation process and a reduction process. So you try to decompose this and this process into simpler processes that can be computed via DFT. And then you relate to what is called a thermodynamic cycle. Okay, so again, these are aspects of thermodynamics. So I'm not going to go a lot into this. For example, see, what you might be interested is in this process. That is metal, there's a solid metal electrode, and you're adding electrons and you're reducing the electrode, let's say, or the opposite. Okay, so what is things in aqueous medium are hard to compute, okay, for very other technical reasons. So what you try to do is you decompose this process into simpler processes. Okay, this is a gas phase atom, let's say. Gas phase atom accepts electrons and gets reduced. Okay, so I can calculate the delta G of this process more easily via DFT. And then this process of gas phase metal forming solid metal, that can also be computed via DFT. So even though I want to compute this process, I first compute this process, and these processes are easily computed. Okay, so that is, I can see, this is hard to compute, let's say, but this process is easy to compute. This process is easy to compute. This process is also easy to compute, let's say. Okay, so I replace this process also easy to compute. Instead of computing this process directly, I decompose this process into simpler process that are computable via DFT and get the energetics of this process. Likewise, I can do this also. This is hard to compute, but these are easy to compute, let's say. Okay, so instead of computing this directly, I decompose this process into simpler process. This is called thermodynamic cycle. Okay, this you might have actually I think from high school you have learned this, that I think it's called Haber process, I think. Okay, in your high school 11th and 12th grade. Okay, you have been taught, okay, the Haber thermodynamic cycle. Okay, so and then the next thing what you try to ask is you try to calculate these oxidation reduction potential. Once you've computed, you try to correlate with certain properties of the electrolyte. So typically these are correlated to the LUMO and the HOMO energy. This is the highest occupied molecular orbital. This is the lowest unoccupied molecular orbital. So there is a correlation that is observed between these potentials to HOMO and LUMO energies. Okay, with this, what is that? You try to, what is the frontier research? What is the, there is a big project called Electrolyte Genome. Okay, all possible, see, we are trying to increase the voltage of batteries. Okay, so lithium ion batteries even. So if you want to go, let's say to very high voltages, let's say even beyond 5, what is the electrolyte that can be used? Okay, which electrolytes are stable? It should not get decomposed because of the anode and electrolyte of the battery. That's the question you want to answer. Yeah, so let me stop here. So just the overview section is a short section. The challenges, there's this last section called challenges and perspective. Okay, so it's a very, this paper, okay, so you should go through this paper carefully. It's a treasured trove of references available. We try to look at three sources. If you think through this, for catalysis, there is this North Coast book. For batteries, this is a review paper which gives you lots of references. And then for separations, we looked at David Schroll's review paper, which again gives you more reference. And there are lots of similarities. Okay, so Sabatier principle, for example, we also saw Sabatier like principles in battery in the previous lecture or so on. Okay, so in challenges and perspective, it's just a summary of what has been already said. So main thing to know is, this is something which I always emphasize to my research students. How, when people ask how accurate DFT is, okay, I feel how much can you rely on DFT? The central question is, if the structure of the system's atomic structure is reasonably accurate. You know the crystal structure, you know the electrolyte structure. Okay, so just one last point I want to emphasize is this electrolyte stability. Okay, in fact, this is very important for this phenomena called solid electrolyte interface, right? So this is a very complex structure. It's not very clear what is the structure of the solid electrode interface. Okay, the ACI, okay, formation. There's a anode ACI is more important than cathode ACI, but there exists both the ACIs. That actually gives stability to your electrode. There's no continuous dissolution of the electrodes. Okay, so, and this ACI is formed by the decomposition of the electrolyte in the first few cycles, right? So that is known. Okay, so the I mean, it's still a very important topic. Okay, why is this still lots of aspects of ACI is not well understood? Because structure is not very well understood. Okay, so the thing I'm trying to emphasize is, if structure is reasonably accurate, DFT can do a good job. Do a good job. Okay, so this is the take-home message. In fact, when people are looking at frontier materials, okay, nanostructures, polymers, we do a lot of work in both these areas. Okay, polymers. There are three materials that are three kinds of structures that are mentioned in the final section. One is nanostructures. I always tell this. Okay, this nano is very fashionable topic, right? If I say, what's your height of your height? What is your height? If you quote the height as 1.69 billion nanometers, okay, people will remember. Okay, so if you just quote it as 1.69 meters, nobody's going to give a damn about your height. Okay, so nanostructures is an important topic because it holds promise for bringing out new properties. Then polymers. Okay, so and then amorphous materials, disordered materials. All three are very important. In fact, all three we explore a lot in our lab. Okay, so in all three, what are the challenges? Okay, so what is the structure? This question is intricately connected to all these things. If you use nanostructure, do I exactly know what is the structure I'm talking about? Which polymorph is present, especially at the interfaces, okay, which you are interested in. Cathodes, there can be more than one structure that is present, and there can be interface. What is the structure of the interface? And this is a grand challenge. Okay, how do I think about amorphous materials? You might have heard something called metallic alloys. Okay, high entropy alloys. So all these things, the structure is not very well known. Okay, so and then there are some of the approximations people are trying to overcome in DFT. Okay, so I would request you to go over this review paper. This is a fairly good overview of the current state of lithium-ion battery. So go through this carefully. That it's not that we have covered everything in this course, okay, but this gives you the big picture, and some of this material, some of you are working for your class project, right? So let me stop here.